In this example we will carry out dynamic simulations to examine the undervoltage ride-through behavior of a group of wind turbines. Activate the study case 6.1 new FRT simulation 0%. As you can see, the grid contains 6 wind turbine models. Each turbine model includes a model of its control system. Let us have a look at an individual wind turbine control system. On the left-hand side, you can see the different slots of the control system. Click on the button Show Graphic to see the composite model frame. This block diagram shows the slots of the model and the connections between them. Notice that the frame of the control system contains several slots for measurement devices. There are also slots for different controllers such as an active and reactive power controller, and a current controller. And here you can see a slot for a protection model. On the right-hand side of the control system model, the network element assigned to each slot can be seen. In this example, we will apply a fault very close to the point of common coupling. This will cause the voltage at that point to fall to zero. The turbines in the wind farm are configured to inject additional reactive current into the network to support the voltage in the event of such a fault. We are going to carry out a dynamic simulation to demonstrate this behavior. The RMS-EMT simulation toolbox should be selected. In the RMS simulation, a three-phase short-circuit fault will be applied. This can be seen in the simulation events queue. It can be seen that this short circuit will be applied at 0 seconds and will be cleared after 100 milliseconds. The location of the fault can be shown in the graphic by right-clicking on the event and selecting Mark in Graphic. The short circuit is simulated at switch bay 3. Due to the fact that there is no fault impedance, the voltage at the busbar will drop to zero. After 100 milliseconds the highlighted switch will open, in order to clear the fault. Calculate the initial conditions. A balanced RMS simulation will be carried out. Run the simulation for 1 second, and have a look at the plot PCC page. The three plots show the variation of various parameters with respect to the simulation time. The top plot shows the voltage at the busbar of the wind farm substation. It can be seen that when the short circuit is applied at 0 seconds, the voltage at this busbar reduces to zero. It stays at zero until the fault is cleared at 100 milliseconds. At this point, the voltage rises back to its pre-fault value. In the second plot, the positive sequence current contributions from the external grid and from the wind farm are shown. It can be seen that during the fault, the contribution from the grid is very high. The bottom plot shows the active and the reactive power contributions from the wind farm. It can be seen that during the fault, since the voltage at the point of common coupling drops to zero, the real and the reactive power also drop to zero. Switch to the page plot Wind Turbine 2.4. Here you can see results associated specifically with one of the turbines. The top plot shows the positive sequence voltage at the wind turbine terminals. It can be seen that during the fault, the voltage falls. But the voltage does not collapse to zero, as at the point of common coupling, because of the impedance between that point and the turbine. In the bottom plot, the active current supplied by the turbine is shown in green, and the reactive current in red. It can be seen that prior to the fault, the active and reactive current are constant. As soon as the fault is applied, there is an initial reaction from the wind turbine, and then the voltage support mode for the fault ride-through begins to exert its influence. The reactive current delivered is determined by the voltage dip and the K factor, and is increased. The active current is reduced, since priority is given to the reactive current injection. Post-fault, the values return to their pre-fault values. Returning to the grid, and looking at a wind turbine controller model again. It is possible to see the parameters which control the fault ride-through behavior of the turbine. For instance, the K factor, which is the gain for the additional reactive current required for voltage support, is set to 2. This can be edited as required. Activate study case 6.2. In this study case, a fault is again applied near to the point of common coupling, but a fault impedance is included, which will result in a voltage drop at the point of common coupling to about 30% of its nominal value. This can be seen in the events queue. Note that this time, the fault is cleared after 500 milliseconds. Calculate the initial conditions and run the simulation for 1 second. In this case, because the voltage has not dropped to 0, there is some active and reactive power transfer. In the bottom plot, it can be seen that the reactive power transfer is higher than the active power transfer.